And let's get started with the intermediate review. So I made the mistake of like not spending all the time on the problems yesterday, and we went really over, and I ended up crashing everything at least once. So let's just dive straight into the first problem here. Here we go. So give everybody a minute to look at this. This is an Amy 14, Amy number 14, which might be difficult. Here. Or was it a 10? If we happen to get done early, which maybe we will, maybe we won't, I'll pick another problem that you guys want. So hopefully everybody's read it. If anybody needs more time, message me because I'm switching over to the whiteboard right now. All right, so here's the equation again. So normally when we have big equations like this that are really like annoying to solve in the general case, we try and look at symmetries. So what symmetries can we find here? I see 3, 5, and 17, 19. What does grouping these do? What does grouping these do? Oh, I see. So a lot of people are saying that y is equal to x minus 11, then these become symmetric. That's an interesting idea. However, I don't think it will be too great in this case because we get rid of this symmetry by doing that. We want to exploit this somehow. Plus x minus x, what do you mean? Group the first and the last, second and the third. That's a great place to start. So let's go ahead and do that. And this was how I started too when I first looked at this problem. So we're going to group these and we're going to group this. So what do we get? Oh, this is nice. We're going to get 3x and 19x. So that's 22x. And what are we subtracting? Negative 3 times 19, negative 3 times 19. That's 114 over x squared minus 22x plus 57. All right, I have another suggestion that maybe we can consider later. We do the same thing here. I'll spare you all the details. And yeah, look, we have all these 22s right here, and we're just like adding another term. The problem is the problem is when we try and combine these, it's not going to be that nice. So we're going to have to use a different trick, unfortunately. I will tell you right now that the path that continues from here is pain and suffering. Y equals 22x, and like one way I can see that is because I look at this 22 and I look at this 11 right here, and that's just weird. And maybe that's not what I want to do. Use the fact the numerator and denominator share the same numbers. How can we exploit that? Because that is interesting, for sure. All right, well, here's something cerebral you can do. Let's take a look at this. We're just adding 1. All right, and it turns out we get x over x minus 3. That's cool. It probably works in the general case too, and you can all see why. So what happens if we add 1 to each of these? That's the same as adding 4 here. So we actually get rid of this term, which means that this side is going to be divisible by x, and this side is probably going to be divisible by x as well. So what happens when we do that? Let's go do that. So what we do is we add 1 to each of these. We get x over x minus 3 plus x over x minus 5 plus x over x minus 17. Finally, x over x minus 19. So now we have this equation. And what is the next step we should do? Anybody see something nice about this equation that's... I see divide by x. Excellent idea. But what if x is equal to 0? It's, I mean, it could be. Like, I think it's a perfectly valid solution that we just showed. But the problem asks us for a solution with this answer format, where all of these are positive integers. So the answer of this form is not going to be 0. So we're actually like sort of cheating right here. So 1 over x minus 3 plus 1 over x minus 5. And you see this already looks so much cleaner. Maybe not so much, but it's a start. So what should we do here? I see combined 1, 4, and 2, 3. Yeah, that's an excellent idea. So now we're going to use that same symmetric argument that we tried before, and hopefully it's going to work out a little better. This was the Amy 2014. I also see a lot of y equals x minus 11. I'm going to refrain from that for now because we can probably work without it, and you'll see why I do that at some point. So what happens when we combine those two? 2x minus 22 over x squared minus 22x plus 57. Oh, I like this. And then when we combine these two, 2x minus 22. This is really nice. That should be a 5. That's equal to x minus 11. So now, I'm sure you all see what we're supposed to do now. See, divided by x by 11. Perfect. What if x is equal to 11? Same cheat as before. We know it's not equal to 11 because this thing exists. So yeah, we're going to get rid of the x minus 11s on both sides and look at what we are left with. So now we have this. And from here, I'm going to actually erase all this work over here because I need the space. So now we're going to need to make another substitution. Take the reciprocal of both sides. That's going to actually mean that that's actually going to force us to combine these, which we definitely don't want. All right, let y be x squared minus 22x plus 57. Yeah, we see this similar term in both sides, and that's excellent. I'm going to be a bit different and go y is equal to x squared minus 22x plus 71. Now, where did I pull 71 from? Well, that's simply the average of these two constant terms. Yeah, so now it's going to look like x minus 14 and x plus 14. And of course, I did not mean x. I meant y. And that's equal to 1. Perfect. So now we have 4y is equal to y squared minus 196. All right, I just combined these two, which was really easy because of the symmetry here. So now y squared minus 4y is equal to 196. And this is just begging for complete the square, so I'm going to do that. Y minus 2 squared is equal to 200. Y is equal to 2 plus or minus square root 200. I'm going to leave it like this just to save a bit of time. All right, so now which solution do you think we're going to want for this? The bigger one or the smaller one? If we want to make x as big as possible. We definitely want the bigger one. So we're going to put the bigger one in here. I hope you all remember what we did here. Just nice combinations. The whole symmetric stuff, you all had that on lockdown. So what do we do? 2 plus root 200 is x squared minus 22x plus 71. So we can do the same thing. Let's actually complete the square. I do not want to do quadratic formula with this. And then we're going to add 121 to both sides. And then this is going to become that, and the other side is going to become 52 plus root 200. So we want the maximum value of x. So we get x is equal to 11 plus. And yeah, they ask us for like a plus b plus c, but who cares? Why did I not simplify? Because these actually don't want you to simplify. When I solved this last night, when I was trying to figure out how to do this, I did simplify, and I realized that I had to unsimplify afterwards, and what's the point? Okay, any questions? Well, if you do, you should direct them to Andrew. So let's move on to the next question. Next problem. Whoops. That is, bam. Take a minute, stare at it. When I first saw this, it made me cringe a little. Why? I'll explain why later. So just as a precursor, does this remind you of anything? No, you got the name right. De Moivre's theorem. I don't know how to pronounce it. So DE space MOIVRE. So let me get the whiteboard up. And this is it. So now it's like de Moivre's theorem, but is it de Moivre's exactly? Like, can we just like plug in de Moivre's and just kill this problem immediately? Turns out we can't, because what does de Moivre's actually say? That's right. What it actually says is cosine of t plus I sine t to the n is cosine so we got our sines and our cosines flipped, and we're going to have to deal with that. Fortunately, this is actually not too bad, because what we need to know is we can actually switch this sign, express this sign as a cosine of something else. How can we express this as a cosine? See, one person was very quick to the trigger. Not 45-degree angles. It's actually going to be cosine of 90 minus t. Technically, you want to be using radians, but who cares? We can do the same thing here. Great, so now we can expand this. And look, we have a carbon copy of de Moivre's. Cosine of 90n minus nt plus I sine of 90n minus nt. But we don't want to compare this to that. We want to compare a sine. This sine is I times the sine. That's just me having bad handwriting. So we want to compare, we don't want to compare apples to oranges. We want to compare apples to apples. So what we're going to do is do the exact same thing in reverse. Take 90 minus this. That actually becomes sine of nt minus 90 times n minus 1. Plus I times the cosine of the exact same angle. Great question. Where did the 90 minus t come from? The idea is that if you have this triangle, and this is like 1, this is cosine t, and this is sine t, then we can express this both as a cosine of this angle and as a sine of that angle, which is how we obtain this equivalence. And then the other ones follow suit. So what do we want? We want sine of nt to equal sine of nt minus that. So let's take a look at this and this only. When is this true for every possible t that we can imagine? When 90n plus 90 is 0. So n has to be equal to 1. I should specify. When is this true in the general case? Anybody just go and jump the gun? All right, so we know, okay, for that cycle, what does that mean? Are there any other numbers for that it's true? We know n equals 1. That's good. Do any other n work? Also 5? Where did you get 5? Oh, because and this is 360. So now if we look at our unit circle, let's just pick a random angle. Let's pick here. And this is the sine. So if we keep on subtracting 90-degree angles, like that, we see that it repeats every 4 times, every 360 degrees. So n equals 9, all the way down to n equals 997. So how many of these n are there? There are actually 250. Exactly 1/4 of everything. And cosine works the exact same way. You can check that yourself. It's a good exercise. So 250 is actually the answer. This was another Amy question. All right, are there any last questions about this? If there are, remember, direct them to Andrew. So let's go back. Let's look at the next one. All right, bit of a breather. This is an early problem from an HMMT February algebra test. Stare at it for a minute, and then we'll get started. Okay, let's get started. Somebody asked, this is solvable. Yes, it actually is. And that's actually really cool. Why? So all the necessary information, forgot to clear this. Q of x is going to be equal to a0 plus a1x plus an x to the n. These are all integers. All right, just know that we're dealing with integer polynomials. That's actually going to be really important. We know that Q of 3 is going to be 20 plus 17 root 3. So let's just write this out. Let's just, oh, I forgot the square root. Let's just write this out. So this is going to be Q over 3 is going to be a0 plus a1 root 3 plus 3a2 plus 3a2 root 3 plus 9a3 plus 9a4 root 3. Hopefully I'm not repeating indices. Plus, I messed up. Thank you for the people who yelled at me. Just 27a6 plus 27a7. Okay, at this point, everybody sees that like we can like ignore these because we know that like these are either going to be like 0 or like 27 or bigger than 27, which is like way bigger than each of these terms. If nobody's responding, hopefully that means nobody's confused. So we can actually just stop the trail right here. So what are we looking at? We are looking at this. And it turns out we can even factor this. Let's group them into integer parts and root 3 parts. Root 3 times a1 plus 3a3 plus 9a5. All right, and this is 20 and this is 17. So whenever we have irrational numbers that look like this, we can like get like a bunch of equations just by comparing like parts. So in this case, we're comparing the 20 parts and we're comparing the root 3 part. So we need to find a combination of a0, a2, and a4 that looks like satisfying these conditions. That's sum to 20. So what can we do? Nobody is answering. One person has answered with an interesting idea. And the idea is base 3. So this actually sort of touches on our number bases thing. It turns out that like this is like the base 3 representation of a number. Like just how we can write a 3-digit number as a0 as a plus 10b plus 100c. You see how like this is like base 10 representation? This is base 3 representation. But another person said something that I liked. We can test all of the cases. Yeah, there are only 27 of them, and most of them you see will not work. But it turns out just to be bash from here on out, so we get 2, 0, and 2. It's kind of boring. And you guys can test that for yourself, but it works. Same thing for 17. You get like 2, 2, and 1. Does anybody want elaboration? Elaboration, I got a yes, so let's elaborate. Okay, so this 9 is really important because 9 is going to take up the majority of this. Like, in fact, even if you make like a1, 2, and a3, 2, all this is going to add up is 8. So this 9 is important. So there should be at least like one 9 in here. So then once we do that, we're left with 8, and from there we can just bash. Think about just like trying out all possibilities and then eliminating the cases that are just like impossibly small. So overall, once we plug these back in, our polynomial is actually 2 plus 2x plus 2x cubed plus 2x to the 4th plus x to the 5th. So what do we get when we plug in 2? The eternal question. Right, I see somebody says 86. I really hope that's right, because I hate doing arithmetic. So yeah, this is what we got. So now let's take a look at how we got here. All right, we just expanded it out, got rid of all the terms that were just like obviously bigger. And then we group them, then we group them, and then we bash. Everybody's favorite trick. Well, yeah, I can hate arithmetic. A lot of people do. This is boring. So let's go on to the next question. Untitled presentation. Bam. Yeah, sequences and series. So stare at this, think about what we're going to do. What is Mildorf? Mildorf is a guy. Thomas Mildorf has written a series of 5 extremely challenging practice AMY tests, which are well known within the lore. And they have excellent problems, like really difficult, lots of ingenuity. So yeah, we're gonna have to solve this. And I like this question. It's magic. This one is pretty light on bash, actually, if we do it right. I don't know if there's a really bashy way to do it. Like maybe some arithmetico geometric sequence. All right, let's go. What? New share, whiteboard. Get rid of all this gunk. And what are we looking at? Sum of n is equal to 1 to infinity of 7n plus 32 over n times n plus 2 times 3 to the n over 4 to the n. So this is scary because we're combining like this, a sequence of this type and a sequence of that type. The trick is we're going to have to focus them one at a time. I define scary as in it scares me, because this is certainly frightening in the general case. We're going to have to hope that there is some trick that we can utilize. So let's say we were, okay, let's consider this. This is nice. That's all there is to it. Let's ignore this. Let's take a look at this. How do we usually solve problems that look like this? Telescopic sums. All right, can somebody remind me what that means that we should do? Partial fractoids. Yeah, let's do that. Let's split this apart. So we're probably going to have like an over n and an over n minus 2. N plus 2, sorry. So it turns out that you can like sort of do this one in your head pretty quickly. What you do is notice that like this is the only one with a constant term. So that this must be the only thing that contributes to that. So this must be a 16. And then we have 16n, and we're left with 7n, so we have to subtract out 9. So we get this. Yay. Whew. How many monitors do I have? I have two monitors. So what are we going to do? We're going to have to expand them. Plug this in. We have this nice information. We should use it. I'm just going to leave it expanded. 16 over n times 3 to the n over 4 to the n. Minus 9 over n plus 2 times 3 to the n over 4 to the n. All right, so now, can anybody tell me what we do now? Because this is really the crux of the problem. Attempts to telescope? Cancel stuff out? How are we going to do any of that? Simplify? What can we simplify? These are all really vague answers. I want steps. Four and 16. I see, try plugging in n plus 2. What does that mean? What do we plug in n plus 2 for? Oh, I see a lot of these observations. Oh, 16 is 4 squared. This is 3 squared. Okay, so we plug in n plus 2. So that means like we go like from n equals -1 to infinity of 16 over n plus 2 plus 3 to the n plus times 3 to the n plus 2. Is this what you're talking about? Minus 9 over n plus 4 times 3 to the n plus 2 over 4 to the... Is this what you meant? Because this actually does not help. Wait, this does not help. I don't see the difference. (16 to the n) 16 and n to the n plus 2 cancel. Oh, what are you doing? You're saying that like we cancel this out, then we cancel this, then we move this 2 over here to become 9. You can't see the edge of the screen. It's like barely cut off. Oh, interesting. Yeah, so what you've done is you've made these two terms equal. So now we have to just add this, and then we get another expression with two terms. How do we handle this? We don't add. What do you, we telescope? I'm having a really hard time following your logic. This is not going, this is doing it like this is gonna be challenging. Let's try and do this. Let's try and follow your idea, except let's do it all within this sum. Yeah, I'm going to just go ahead and present the solution that I'm most comfortable with. So we're going to split. So the way that I found this is I noticed, hey, look, all of these are n. That's really nice. That's like symmetric, but this is not the same. Maybe we can do this. And this is basically what you were getting at. So let's multiply by 3 squared over 4 squared and by its other. This is really cramped. I'm sorry. All right, so when we combine this, this becomes 3 to the n plus 2 over 4 to the n plus 2. And when we combine these two, that's where the magic happens. So 16 over n times 3 to the n over 4 to the n minus 16 over n plus 2 times 3 to the n plus 2 over 4 to the n plus 2. Now, this is something that will telescope nicely. All right, and how did we find this? We just look. Wow, this is really nice. I wish that we could do this for the other side. So n equals this pod, like what we're adding here is going to be n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, so on. What we're subtracting is like this term is equal to 3, 4, 5, 6, 7, 8, 9, so on. So once this is all said and done, we just substitute 1 and 2, because those are the only things that won't cancel eventually. And this is an Amy, so I'm going to be not rigorous like this, but you should all know that this is what I just did. I skipped a lot of steps that you should be very concerned about. But we can evaluate this, and we get 33 over 2, I think. What did I multiply by to get the second thing? Okay, basically just like if you expanded this, you'd see that like everything cancels except for the first 2 terms. How did I get from here to here? I wanted 3 to the n plus 2. Oh, from like, wait, are you talking about 1 to 2, Gabriel? 0 to 1? Oh, how did I get from here to here? Okay, this term carries over. This term, I wanted a 3 to the n plus 2 over 4 to the n plus 2. So I multiplied by 3 squared over 4 squared. Then I multiplied by 4 squared over 3 squared to cancel. So then I combine these two and I combine those two and I get that. The answer should be 33 over 2. Maybe I did wrong math, but this is the method and that's all I care about teaching to you. Okay. Sorry, we got to get going because I also have to leave at 4 today. And it's even more urgent this time, so let's take a look at this. Just stare at it for a minute. What is IMO? IMO is the International Math Olympiad. Why do we have class on July 4th? Scheduling happens. Math stops for no man. So yeah, this is a problem that's the top people in the world have to face, and we are going to destroy it right here, right now. And it's a really scary looking. It's a really scary looking one. Because like we have the strict inequality, and strict inequalities aren't really seen. And we have like all these like increasing powers, and that's weird. But this probably means this is also a clue for us. Because if we can't mix these, we're going to have to look at each of them separately. And to the n, thank you very much. So we're going to have to take a look at each of these individually. So let's look at 1 plus a over k to the k. Where do kth powers come up in like any of the inequalities that you know? Power mean, that's interesting. Yeah. So this is sort of like the power mean. So let's remind ourselves, what does the power mean say? So if we have like numbers like a plus b plus c over 3, is it going to be less than or equal to the square root of a squared plus b squared plus c squared over 3? Is this what it is? I forget. This does not seem true, but yeah, no, never mind. It is. But it turns out this does not help us here. So I've always had a really hard time motivating inequalities, both for like solving them and when like I'm trying to tell people how to do them. So I'm just gonna give away the answer. It's AMGM. So let's try and see how we can make this look like AMGM. So we have a kth power here, and that sort of corresponds to a kth root on the other side of a product. So we need k terms here. This is one term, but there's only one other term, and we're going to need to get other ones. So the most natural thing to do is just break this up into pieces. So we're going to look like this. And what is that going to be equal to? The kth root of their product. AK over k minus 1. And how many of these are there? Anybody confused about how I got this or the fact that this works? Okay, I'm gonna hope that we're all good. So if we like expand this and like do some stuff, we get 1 plus a to the k to the kth power is gonna be greater than or equal to ak times k to the k over k minus 1 to the k minus 1. Yes, it is a direct application of AMGM. So now let me ask you, what is the equality case for this? Write it over here. Equality. When does that happen? All of them are equal. So what is A of k? A of k is equal to 1 over k minus 1. I'm going to have to change. I realized I made a small typo in the solution that I typed up. So, okay, cool. So let's just apply this for every single one of these and see what happens. So when we multiply them together, we get this on that side. And then what do we get? What do we get over here? Well, we're going to get every single variable. So A2, A3, all the way up to AN times when n equals 2, 1 to the 1 over 2 squared times 2 squared over 3 cubed, or all the way up to n to the n over n minus 1, the n minus 1. And this is magic because this is 1, and all of these cancels. We have telescoping all over again. So after all that work, we've gotten this. Are we done? We're not done. We need to show that equality does not occur. But this is easy because the equality cases for each one of every single one of these is going to be like A2 is 1, A3 is 1/2, AN is 1 over n minus 1. And when you multiply all these together, you don't get 1, which is the given condition. So at least one of these equality cases is going to be false. So we can get rid of the strict and make this strict. Right, great. So hopefully if you have any questions, let Andrew know. I'm going to have to go fast on these last two. But fortunately, these are nowhere near as bad as the last question, on the second to last question of Mondays. So let's solve this. And actually, yeah, I'm just going to go straight to solving it. I will rewrite the expression. Ooh, 133 to the 5th. What were the other numbers? Plus Oh, no. Okay, good. My computer was going very slow and I was about to crash. Fortunately, that did not happen. All right, so the general thing that we're going to do is we're going to bound this, like limits our range by a lot, and then we're going to use mods, which is how these like impossible equations are going to be done. So what do we know about this? This is big. I make the audacious claim that n is greater than 133. And hopefully you can all see why that's true. All right, so now upper bound is a bit trickier. Upper bound is a bit trickier because we have all these. So I'm just going to say n is going to be less than 133 times the fifth root of 4. All right, just imagine like each of these was a 133, and then we just took the root of that. But this is not going to help us because we need to approximate fifth root of 4. You can see that fifth root of 4 is going to be less than 4/3, actually. Just raise both sides to the fifth power, and it works. So it turns out that we get that n is like less than like 177, I think. Or 178, maybe. I don't remember. Anyway, n is like going to be between 134 and like 177.
I think, all right, so Justin has told me that he has crashed for like the last two problems. So I guess I will be in charge and like he has to go. So I guess I'll be in charge of the last two problems. So I don't really have anything to write with, but I'll try my best. I can just type on my computer. So the second to last problem is, let's start again from the beginning. So we have the equation. Let me type this equation out. It's 133 to the fifth plus 110 to the fifth plus 84 to the fifth plus 27 to the fifth equals n to the fifth. And it's asking us to find the value of n. So, all right, so what we start over here, we want to think about like mods and whatnot. Like as Justin said, like mod 3 seems like the most natural one, as 84 and 27 are both divisible by 3. So let's try this one out. So mod 3 gives that 133 to the fifth is congruent to 1 to the fifth mod 3. So it's just 1. 110 to the fifth is congruent to 2 to the fifth mod 3, and that's just 2. So 1 plus 2 is congruent to, I don't have the congruent symbol, so I'll just use this one. Pretend there's 3 lines here. Equals n to the fifth mod 3. So this is just equal to 0. So we know that 3 divides n, or n is congruent to 0 mod 3. Now, the thing is there's a ton of numbers like this. So let's think about this a bit more. So let's look at this mod 10 next of all, as in like looking at the last digit. So if you look at the last digit, this is 3 to the 5. So that's just 3, because 3 to the 5th is 243. 0 to the 5 is just 0. 4 to the 5th is just 1024, so it ends in 4. And 7 to the 5th is 79317. So it's just 7 again. So this is congruent to 4 mod 10. So we see that n to the 5th is congruent to 4 mod 10. So what digits can n end in? Yeah, the only digit that n can end in is 4. Like if you just plug them in, you know n has to be even. 2 becomes 2, 4 is 4, 6 becomes 6, and then 8 is just 8. So yeah, n has to be congruent to 4 mod 10. So we now know what n is mod 30, that n is congruent to, using these two equations, we can determine that n is congruent to 24 mod 30 using these two equations we've gotten. Now let's do a bit of bounding because we already have like a pretty good idea of where n is. So we know that n is greater than 133, of course. N greater than 133. But then let's take a look at this a bit more. We know that n is smaller than 133 times the fourth root of fifth, right? Fourth root of fifth root of 4. 133 times, I kind of screwed this up a little bit. Let me select this text. Yeah, fifth root of 4. So we have this, right? So then from here, we know that we can kind of like sort of create a bound on this. From a bit of trial and error, we can determine that the fifth root of 4 is less than 4/3. So that fifth root of 4 is less than 4/3. Shouldn't it be the fourth root of 5? No, because if you think about it, it's like this thing is less than 133 to the fifth times 4. We're just creating another bound because we know that this over here is less than 133 to the fifth times 4. So we take the fifth root of both sides here. We can obtain this bound over here. So then from there, we know from here, we can do a bit of trial and error and determine that fifth root of 4 is less than 4/3. So that's a bit more of a bound. So now we have that n is less than 133 times 4/3, and that's equal to approximately like, let me calculate real quick, like 178-ish. So now, like 177, 178-ish after calculating. So now after this, we can determine what n is because we know n is between 133 and 178. Now let's look at what n mod 30 is. So we know 133 mod 30 is 13, and 178 mod 30 is equal to 28. That means that n is that means that there's two possibilities for n equals 144 or n equals 174. So narrowing this one down is pretty easy. Like let's take a look at this. Let's take a look at this from another perspective. We know that 144 is like a lot closer to this, while 174 is really, really close to this upper bound. In fact, like 27 to the fifth is like so minuscule in comparison to 133 to the fifth. We know it can't be this close to 178 to the fifth. So although this is like a little bit of like, I guess, more hand wavy, it's a form of estimation. And like we reasonably know that 110 to the fifth plus 84 to the fifth plus 27 to the fifth is a lot less than 133 to the fifth times 3. So we know that they can't be this close to 170 and can't be this close to our upper bound, which is 178. So we can reasonably cancel out 174. Of course, you can also apply a few more mods to determine what n really is. But for the sake of time, I'm not going to do that. And instead, here's a good trick, a bit of practice and estimation. Someone asks how I got the fifth root of 4 over here. Well, we know that, again, this side, 133 to the fifth plus 110 to the fifth plus 84 to the fifth plus 27 to the fifth, that's less than 133 to the fifth times 4, because like each of these terms is less than 133 to the fifth. And then now we know that end of the fifth is less than 133 to the fifth times 4. So we can just take the fifth root of this entire equation to determine that n is less than 133 times the fifth root of 4. Now, yeah, the answer is 144. And again, we can just use are nice estimation tactics to determine that it's not 174. Now, I think, so we finished this problem. Now let's go to the last problem. Let me create a new page over here. So this problem is 2018 Amy 1, number 11. So the question text is, find the least positive integer. Can y'all see what I'm typing right now? When 3 to the n is written, all right, in base 143, its two rightmost digits in base 143 are 01. All right, thanks everyone. So anyways, yeah, here's the last problem. I'll give you all a few seconds to look at it, like 30-ish seconds to read over it. And yeah, I'm gonna go quickly for the sake of time since it's already 4 o'clock. So only about like 5 more minutes, don't worry. All right, so let's start going through this problem. So let's look at this condition first. It says that the two rightmost digits in base 143 are 01, which means we know that 3 to the n is equal to like 143 times, like 143 squared times some number, let's say k, let's say a plus 1. And this is just translating our condition into like base 10. So let's take a look at this. That totient function, we're going to be doing a slightly, like a more mod-based solution. So this condition implies that 3 to the n times, so we can translate this in terms of mod 143 squared. So 3 to the n is equal to 1 mod 143 squared. Someone asked why 143 squared? Well, we're just looking at the problem statement. It says the two rightmost digits in base 143 are 0, 1, which means that like the other digits to the left must be something 143 squared. Now, for 11, okay, so you know that 143 is equal to 11 times 13. So 143 squared equals 11 squared times 13 squared. Now what? Let's take this mod 11 squared and mod 13 squared, and then we can combine those two. Well, we know from this condition that 3 to the n is equal to 1 mod 11 squared. That's what we want to find what n is. And if we just start expanding the powers of 3 out, we know that 3 to the 5th equals 243 is congruent to 1 mod 11 squared. So we know this, which means that 5 satisfies the 11 squared part of our equation, our modular equation. Now let's look at the 13 squared part. So we know that 3 cubed, first of all, we know that 3 cubed is congruent to 1 mod 13. We know this isn't mod 13 squared, just mod 13. But we know the exponent must be a multiple of 3. So let's keep going and figure out what's right. So we know that, let's actually take 3 to the 3k power. Because again, we know the exponent for 3 to the, because we want to find some number like 3 to the t equals 1 mod 13. We want to find t. So again for this, we can just examine 3 to the 3k because we know 3 cubed is congruent to 1 mod 13. So 3 to the 3k must be congruent to 1 mod 13 as well. In fact, let's look at this mod 13 squared. So this is equal to 27 to the k, which is equal to 2 times 13 plus 1 to the kth power mod 13. Let me move this a little bit. And remember, mod 13 squared, sorry. So we're looking at this whole thing mod 13 squared. And this is just equal to 26k plus 1 mod 13 squared. And this last step we have here from expanding from 2 times 13 plus 1 to the kth power to this is just because of binomial theorem. If we expand it out, the last two terms are 26k plus 1, but all the other terms are divisible by 13 squared. So now we know that 3 to the 3k is congruent to 1 mod 13 squared. Only if and only if k is congruent to 0 mod 13. So we know this thing. And from earlier we know that 3 to the n is congruent to 1 mod 11 squared if and only if k is congruent to 0 mod 5. Because again, we have here that 3 to the 5th is equal to 243 is congruent to 1 mod 11 squared. So what does this tell us? This tells us that the exponent is divisible by both 5 and 39. Divisible by both 5 because the 11 squared part and 39 because of this part, the mod 13 squared part. So from here, we know the smallest possible integer n is going to be n equals 5 times 39 equals 195. And that's our answer. If you have any questions, ask me now because I'll be ending the meeting in around like 1 minute or so. Just read over this and make sure you understand the solution. All right, so someone asked, how do you do with totient? Well, I think the solution will be a bit more. Actually, I don't know if we can actually do this with the totient function. I think most likely we just have to, because the totient function wouldn't be the least positive integer n. It would just result in a positive integer n. So I think the best, again, like the best way to do, maybe it could be done with like a lot of computation, but honestly, that would just be a roundabout way for doing it in this method, which is just to like decompose 143 into 11 and 13, and then look at these separate mods. Somebody said, why is the exponent divisible by 5 and 39? Well, we know that this is congruent to 1 mod 143 squared. So we can decompose it into 11 squared and 13 squared. We know that 3 to the 5th is congruent to 1 mod 11 squared. That's the smallest number that is. And 3 to the 39 is congruent to 1 mod 13 squared. That's also the smallest number that satisfies that. So that means that if for some n such that 3 to the n is congruent to 1 mod 143 squared, we know that 3 to the n has to be congruent to 1 mod 11 squared and 13 squared. So 5 and 39 both have to divide n. All right, so I gotta go now. So I'm just gonna end the meeting. Thanks for coming, everyone. Sorry for the technical difficulties, and we hope you come next week. See ya.